Achha, thank you. No, it is not on, I think. Yeah, it will work now. Thank you. Good morning, all of you. Yeah. So, yesterday we had 2 lectures on introduction to the transportation geotechnics, climate resilient transportation geotechnics, the need for such a concept, and also we had a discussion on the state variables. We discussed that state variables are the dependent variable in the governing equations, fundamental equations. So that's how the void ratio, stress, all of them are the state variables. So this is coming from a continuum mechanics concept. So then we discussed suction could be the ideal state variable representing unsaturated soil behavior. Of course, the moisture content is also one of the state variables. Now, these 2 state variables constitute a relationship. Changes in the suction with moisture content is one of the important constitutive relationship that we need to develop. And we had a lab session yesterday. So, in the lab session, there was some discussion on the measurement techniques. Although we could not give the background to some of the measurement techniques for these state variables, I will try to do that today after describing the constitutive relationship. So, yesterday it was said that the suction is nothing but soil water potential, which is a combination of matrix potential, osmotic potential and adsorptive forces all put together. It constitutes a matrix suction. When salts are present in water, again the potential is dropping, which is contributing to osmotic suction, which is slightly different from osmotic potential what we described in matrix suction. Nevertheless, put together you have called something called total suction. Total suction is a positive quantity. How much is the potential drop with respect to atmospheric conditions? Atmospheric pressure, you may have 101.325 kilopascal air pressure. So, with respect to that, how much it got dropped, that is what it is describing. So, in terms of head it may be negative, but when we describe in terms of suction, which is UA minus UW, therefore it is a positive term. So, that is how in geotechnical engineering we adopt. So, in generally water resource and other soil science areas, they use suction head or soil water potential in negative sign, but we use suction in positive sign because it is with respect to UA. So, therefore, which is used in positive term. There are some advantages when you are using some empirical models using UA minus UW concept or suction concept. So, I will try to describe more about this suction so that we will be very familiar with what suction and what we are talking about. If I take a capillary which is completely filled with water, and if I have a capillary which is open both sides, if I just keep it in hand, water will not drop out because capillary is very tiny and the surface tension which is acting inside or the potential drop because of which the water is actually existing inside, which will act against the gravity. So, it will not fall off. Even if you take a thin capillary which is given for stirring your coffee, right, after the capillary rays if you take out, it will not drop out unless until you tap it, right. So, it is actually acting against the gravity. So, that is the condition in the first case. If you give some energy or try to suck the water from it, right. So, what happens exactly is that it seems water will not be sucked out immediately. It tries to bend, it tries to become curved. right? It's called receding angle. It is kind of becoming like this in the second picture. Slight water content might decrease, but it is fully saturated because air hasn't entered in it. Only the meniscus angle got changed. So further, if you try to draw, then it may have to give up and then start dropping. So which is where the water is getting replaced with air. So why in the second and third cases only angle is getting changed but not water is dropping down? That is because it has some interactions, right? Adhesive interaction between surface of the capillary tube and water molecules. So because of which it doesn't want to get out of the capillary. So which still has, he is trying to hold the capillary tube inside, and but still, because you are giving some energy, some part of it is actually getting evaporated. That is what is happening, right? So what does it mean? If I try to represent in terms of a graph with respect to suction, on x-axis, suction on x-axis or negative pressure, right? I am trying to decrease the potential. Therefore, suction is what I am trying to decrease the potential inside it. So therefore, water is coming out, right? So when I am doing this should happen on both sides, in fact. Okay. So that is how it should happen. So water is actually coming out, and here the air entry started into the capillary tube. So if I try to draw the volume of water present in a tube with respect to negative pressure, this is how it represents. It tries to drop like this, but at this point it suddenly drops because air has entered here, right? This is how it represents. This is what with one simple capillary I am showing you, right? Yeah, sorry. If I do that with several capillaries attached together, something like this, a bigger capillary with a bigger radius and capillary with the smallest one, and in between you have a number of these things, right? Again, now this particular capillary network got completely filled with water in the beginning, and I am trying to draw water. So water will be dropped from the largest pore first, correct? Largest pore has lower potential, so water will be dropped from this. So if I do that, if I continue the same thing, water will be dropped here, and then slowly even thinner tubes will give up, right? So in fact, our soil pore network can be can represent or can be mimicked by this kind of a simplified structure, which will be much complex, of course, where you have number of pores connected at any given cross section. So that could be described with a number of capillaries attached to each other at a given section, cross section. So now, if this can be plotted on x-axis, you have a negative pressure, negative pore water pressure. On a y-axis, you have volume of water or volumetric water content we say, which is volume of water by total volume. So we are accustomed to use gravimetric water content, which is mass of water by mass of solids, but in unsaturated soil mechanics we use volumetric water content for a reason which I will describe after some time. This is volume of water by total volume, right? So if this happens, the curve looks something like this, where initial drop in one of the capillaries that happen like this, and next smaller one, smaller to the largest pore, that actually drops here, and the finest pore gives up at somewhere. If you combine this, you will get a interesting relationship, kind of a S curve, which is called soil water characteristic curve or water retention curve. So this is exactly what happens when soil mass, saturated soil mass is exposed to some atmospheric conditions. That is what we do in shrinkage test, right? In shrinkage test, we try to mix the soil with water and keep it in the atmospheric conditions under some RH and temperature. Then evaporation takes place. Why evaporation takes place? Why evaporation has to take place? Because the vapor pressure difference or the energy difference. In the last class I mentioned about Kelvin's equation, which relates RH, temperature and suction. You can understand what suction are the potential which is available in the atmosphere. We know the RH, we know the temperature, we can evaluate. So that is the suction in the atmospheric conditions. And you have a saturated soil mass where soil water potential is 0, right? So there is a difference in the potential. Therefore, there is an evaporation that is taking place. It is giving away water. If a dry soil mass from oven dried, after cooling down, if you keep it outside, it tries to absorb moisture from the atmosphere because there is a potential difference that it is trying to equilibrate with, right? So there is an exchange of mass that is taking place because there is to balance the energy, right? Same thing is happening, you know, I am not sucking literally, but evaporation is taking place. So therefore, this is what is happening. So this relationship describes how fast the pores are giving up, or how large the pores are inside, or how small the pores are, and how the geometry is actually existing. Because previously, if you see, there is only single capillary. If I can make a material with symmetric pores of same size, the relation should look like what it was like this. Like in case of filter paper, you may have uniform pores or porous discs. They may have a relation something like this. But in case of soils, any heterogeneous material having heterogeneous pores all across distributed, you may have a relation something like this, right? S curve. Your particle size distribution curve, any curves you take in soil mechanics, they follow the same trend. So essentially, even effective stress versus void ratio, the relationship looks similar, right? In effective stress versus void ratio in a consolidation test, you are applying a pressure and volume is getting compressed, right? So you are representing void ratio with respect to effective stress. Here also volume might get changed if it is an expansive soil and evaporation is taking place, so suction is there. Both can be plotted together, but both represent S curves, but they differ. That maybe we will discuss later on, right? So there you are applying a mechanical pressure, here we are applying force, which is suction, right? So that is the difference. Now, if I have a soil column, so it is a more realistic, right? The soil column which is placed in a water reservoir. So what happens? Water anyways would be there up to this level, but then beyond that there is a capillary raise that takes place, and there is a capillary raise, and maybe this is the point where this is a section where all pores are below that, all pores are fully saturated, right? Above that they may not be, because you may have different capillaries attached to individual sections. Beyond that, maybe a larger pore is getting exposed and air is entering into it. Thinner pores still they are saturated. So combination put together, this is partly saturated. Some pores are fully saturated, fully filled with water. Some pores are emptied by air. Therefore, at any cross section beyond this, soil is partly saturated, right? So what is this called? Capillary raise and air entry head we can call. So beyond that, air is entering into your system. Until then there is no air. You cannot see individual capillaries separately here. Here soil means together, right? All capillaries put together. Just like in the previous illustration where number of capillaries are attached to each other. Similarly here capillaries are attached. So therefore beyond this, soil within the soil pores air has entered, so which is called air entry suction, or this particular height is called air entry suction head or capillary rise simply. Beyond that, capillary fringes are there, partly it is saturated because thinner pores might have received more water, and that is how they are. And after very long distance from this or height, you may see that it may be completely dried also, depending on the type of soil, right. And this process also is a time taking process, it is not instantaneous because it depends on hydraulic characteristics, permeability or the hydraulic conductivity, how fast they can go up, right. So if I describe the soil water characteristic curve, so this is UM minus UW, right. So how much water pressure has dropped or potential dropped against a reference potential, reference pressure, that is air, that is UA minus UW, which is a positive value. We give a sign something like this, psi, suction, which is representing suction in kilopascal only. Generally E versus log P in logarithmic form we represent because the ranges are too high, right. So we also represent in terms of in logarithmic scale, okay. These are in logarithmic. Anyway, so this is in logarithmic, and this is theta, which is volume of water by total volume, right. So the curve may represent something like this. So theoretically I am just plotting, but you may have a number of data points when you do an experiment and measure it, right. So often this is thought that this is the air entry value, or for a better understanding the air entry value you should represent in terms of degree of saturation. So there is a relation between theta and degree of saturation, we can convert because anyways the density is known. In fact there was a question yesterday also, you can always convert gravimetric water current to volumetric water current to degree of saturation if you know the volume of the soil mass. So volume of the soil mass has to be known, density, rho d, dry density should be known. So then we can convert from W to theta, and from degree of saturation everything can be done, right. So because void ratio is required for that, so rho d is required and we can convert easily. That is how we obtain in terms of degree of saturation or in terms of volumetric water content. So degree of saturation, it represents something like this, because until here soil is fully saturated and then air has entered here, which we call air entry value or air entry suction value, and after that it larger pores are giving up, and then thinner pores are giving up somewhere here. Again you have another bend which we call residual water content somewhere here, and after that the decrease is very negligible because thinner pores are getting emptied over here, their contribution is less in the total mass of water. In total volume of water their contribution is less here, right, because only thin very tiny pores are present here, are still saturated or maybe partly saturated, and they are giving up the water here. So the contribution is very less. If you change a suction from here to here, the change in the water content is very small, tiny, but for the same change in the suction here it is a huge variation in the water content or degree of saturation, right. So this is a very important constitutive relationship which is a backbone for understanding many concepts, many engineering concepts like shear strength variations, hydraulic characteristics, volume change, anything you talk which is directly is influenced by soil water characteristic curve, or we can in fact correlate different characteristics using the SWCC or WRC, whatever it is. So in general, the air entry of sands is around 2 kilopascal. Okay, so beyond that it quickly desaturates, and for silts 100 kilopascal. It's a kind of a rough estimation. It's not a accurate values. For a given soil, you may have a uniform sand or well graded sands, etc. Right? So in that case, SP, all those things, things will change. Obviously, SP will have slightly less compared to well graded. Right? Well graded, it will have pores of smaller size as well. Right? So it will try to take you to larger suction, air entry suction values. So silts generally around 100 kilopascal or so, and the clays can vary to even MPa, megapascals. Right? So theoretically, how much it can go to, how much maximum suction can exist. There was a theoretical work given by Fredland. He mentions that it can go to 1000 MPa theoretically from thermodynamic perspective. So 10 power 6 kilopascals, sorry. It can go to 1000 MPa, it seems. Okay, so we don't require up to even 1000 MPa for even bendonites. Even 20, 30, around 80 MPa or 90 MPa almost will come to here. So we can guess what will happen, right? So I was trying to describe in a natural system, you have a ground surface here and groundwater table here. This is the groundwater table, this is the ground surface. Right? Now there is a capillary raise. Capillary saturation takes place. Capillary saturation takes place, and this is a capillary raise. And beyond that, this is how it changes. Even SWCs can be drawn here. So this is the suction, because there is a negative pressure. Here the potential is 0, correct? So beyond that it's a negative pressure, negative potential. So water content changes in this manner. So this is a theta S, saturated volumetric water content, and which almost is constant, slightly might decrease. So beyond that it starts decreasing, because area has entered here, right? Up to here it is fully saturated. Remember, although this is fully saturated, there is a suction, right? So there is a negative pressure in this. Just like when you take a beaker of water and insert a capillary in it, so you have a capillary raise. There is a capillary raise. What is it? नीचे तो नीचे कर दीजिए ठीक है I'm sorry so this is the water in the capillary so this is a point where you have the zero potential and the potential is decreasing continuously right. So within this capillary the water potential is negative, suction is negative, but it is fully saturated, there is no doubt about it, there is no air in it right. So that is what we are talking about here. Although within the capillary rays or up to this particular height the soil is fully saturated, there is a negative pressure or suction within it. So this is what I was describing, and in the previous case I was describing a drying phenomena right. There is a drying phenomena that is taking place where I was trying to suck the water from the initially saturated conditions, but here although a similar concept was described, but here initially the soil was dry and it got wet because of the capillary rays here. So this is a wetting phenomena that is describing. For the same soil we can obtain the relation between suction and volumetric water content through drying process and through wetting process. Interestingly, they both differ quantitatively for the same soil. That means it has a hysteresis right. Hysteretic effect is there on soil water characteristic, the suction versus degree of saturation or theta or whatever right. So that is because of number of reasons. So I don't know whether I will get that much time to describe today. So this is what I was telling. There are some characteristics like this is the air entry value, this is a residual water content right. So this is the condition of the soil at different states. This is a saturated state and this is the residual state. Residual state, thin water film is present around the soil system, or any thin pores are there, water might be there. So that is the condition it is in. So for different soils, the soil water characteristic might vary in this manner. So for example, one particular suction if you take, sand completely got desaturated for this suction, clays still fully saturated for the same suction right. So air entry is differing for each soil somewhere here. So for the same suction clays would have been fully saturated, sands would be fully dry right. So suction is the one which plays a role because that is what is the energy, that is what is the potential right. So if you bring two soils together, the exchange of mass depends on the potential of individual things. Yesterday there was a discussion with Bharat, plants, wilting point of the plants. Plants have certain capacity to draw water. So if the capacity of the soils for holding the water is exceeding the capacity of plants to draw the water, then they wilt. Because in black cotton soil or expansive soil, most of the plants would not survive because of the same reason, because they have higher potential. So they will not give up water that easily. So if you plant something which will not be able to take the water because of the suction difference, this has a very strong potential, it will not give up the water. If you keep these two things together, sand and clay, obviously clay will take the entire water, sand will get dried right. So this is the drying wetting curves. Wetting curve, for the same suction water current will be less all any given time. So this is the initial drying and initial wetting, and then you will have a hysteresis curves, loops okay. So there are a number of reasons why you have hysteresis. One is because of the poor network, and we also call ink bottle hysteresis. And for the non-curved surfaces, like which is very common for in soils, the relationship earlier 2Ts by R gets converted to this particular form. And from there, how the estimation can be done, can be understood theoretically. Theoretically, you have some models which are for ideal conditions, highly ideal conditions. These equations are available, these models are available for estimation of SWCC. Because I wanted to actually describe simplified methods for evaluating the SWCC, right? So there is also part of the syllabus that has been given. So here these are some of the models which can be evaluated for idealized cases. I just simply give these slides to you, but you can get back to me if you have any questions. But these are too theoretical, they will not match with realistic soils. So I generally teach this to build a theoretical understanding how to bring a model, right? So I'll actually describe one particular model which is called Arya-Paris method. Arya-Paris method is around 1981 or 80 this was given. From the particle size distribution curves, we can evaluate how the SWCs can look like. Qualitatively they are amazing, they can represent SWC variations very well, but quantitatively there may be slight difference that might happen. There is one single model parameter in a small range. If you use that, you can predict the SWCC. So essentially Arya-Paris method is based on the grain size distribution curve. Both are S curves, interestingly, the particle size distribution as well as SWCC, right? So from here we are trying to predict the soil water characteristic curve. So why SWC is required? We are having many participants from industry. In landslides, for example, if you want to understand how the failure is happening, first and foremost thing I think we should have SWCC, right? Because when the wetting takes place, how the suction is changing. From the suction you can evaluate how the shear strength is changing. So when shear strength is changing, the factor of safety itself changes. We actually evaluate temporal variation of factor of safety with incessant rainfall, with a continuous rainfall which takes place. Using several evaporation infiltration models, we evaluate how the shear strength is changing within the soil mass. Based on that, we evaluate the factor of safeties. Factor of safety is now a time dependent thing with change in the moisture content. So we can in fact predict when the landslide is going to take place. We have done that study in fact for Shillong Nehu site previously, which is published. Right, so these predictions are possible. These are physics based predictions. They are possible once we have a good understanding, solid understanding in soil water characteristic curve. Secondly, the flow characteristics. When the flow takes place, infiltration takes place into the ground, or evaporation takes place, you require drying, wetting SWCCs. Without that it is not possible, right? So the flow characteristics can be understood using this itself. So that's why understanding for a given soil, these characteristics are important. So the grain size distribution curve, if you have, we make number of segments. So this is a segment 1 to say n number of segments. If you make more finer segments, it will be more accurate, right? So from these segments, we have certain relationships like determination of void ratio. Void ratio from the dry density we can determine. This is the GS, specific gravity, or the density of solids. From the specific gravity we will get the rho s, and this is the dry density. Knowing the void ratio we will get the dry density, right? So having that, or MS by total volume, that way also you can determine. So then you can determine the pore volume for individual pores, individual segments. So I segment, the pore volume can be determined using this. So this is the percentage finer calculation from n plus 1th segment to nth segment. So based on the void ratio and rho s input, you can determine pore volume for individual segment. and the volumetric water content can be determined by this one divided by the bulk volume, that is 1 over the rho d, and summation of those things, right. So this way you are actually joining all the pores, initially starting with one particular pore. It's a accumulation of all different pores. That way you will get the theta, volumetric water content. And similarly, pore radius can be determined using this, where you have the volume of the radius. Radius is considered to be, pore radius is considered to be spherical. Based on that particular assumption, this equation has been given, and void ratio is there, and n can be determined from this, assuming that it's a pore is a spherical pore, and using that you can determine the pore radius, and substituting the pore radius in the suction head calculation, you will get the suction. So in this you require cos beta, which is a angle, contact angle, and with that you will get the H value, head. So for a given pore you can determine the suction head and you can determine the pore volume. So the tutorial is not present for this, but tomorrow onwards, in the second half, you get a good time. So please do try this, because the slides will be given today. Already the printing is, for the printing these slides have been given. So we are available any afternoons. So please do come back and do solve this. This is very interesting, and you can in fact try to qualitatively understand how the SWCs can change for different soils. So this is how the values change, and so this is the measured data, and close prediction is possible. So we predicted these things for different parameters, alpha values. Alpha values do not change significantly. So small variation, this is how the predictions can be possible. So we also did for different type of soils, starting from well graded soils to gap graded soils. This is how the particle size distributions vary, and for the same thing, this is how the soil water characteristic curves change. So if you have a uniform soil something like this, right? Look at the corresponding soil water characteristic curve. So for the uniform soil, uniform coarse grained soil, this is how the SWC is varying. So this is the air entry value, right? Air entry is less, around 1 kilopascal for the coarse grained soils, and quickly desaturates. By 10 kilopascal, it is completely desaturating. Correct? If you take uniform fine grained soils, the suction may be, air entry suction may be increasing, but desaturation is quick. Well graded soils, this is a well graded soil. So look at how the SWC is varying. It is going up to nearly 50 MPa, right? That is getting desaturated there. So there is a beautiful relationship between particle size distribution and soil water characteristic curve. There are a number of assumptions made in this, right? Still, a very good qualitative representation of SWC is possible. There are a number of models developed even after this. But this is a first of its kind where relation between these two have been drawn, right? So this is the equation representing transient flow behavior in partly saturated soils. I think Professor Claudia will be describing these Richard's expression. I don't want to derive or describe these models, but I just want to actually inform that there are state variables or dependent variables if you see in this expression. One is matrix suction head or suction, other one is hydraulic conductivity and matrix suction. So these two are required to be determined. Moreover, they are in functional form. K is a function of hydraulic conductivity is no longer a constant value as we do it for saturated system. As it is partly saturated soils, which is dependent on matrix suction head or suction. Similarly, HM is also dependent on something else, right? Sorry. HM is also dependent on something else, right? That is theta. Right? So the variation of HM with respect to theta is nothing but soil water characteristic, suction versus theta. That's what we've been describing so far. So this is hydraulic conductivity variation with respect to either suction or volumetric water content. So these two constituted relationships are paramount important for evaluating the suction head or suction variation with respect to space and time in transient conditions, and R theta versus theta variation with respect to space and time, right? So for example, there is a flow that is taking place against the gravity here. How much time it takes to understand R at any given time, how this profile is changing. This is with time t1, t2, t3, right? With time the profile itself is changing. So this may be the capillary raise in the beginning, sorry, this is the capillary raise in the beginning, then this is the capillary raise, this is the capillary raise, finally this is the final capillary raise, and this is how the transient flow is taking place. This can be understood, the spatial variation of theta or suction, using this particular expression. This is a transient expression called Richard's equation. Very old, 1911, but still it is in use. Fine. This again uses mass conservation of mass expression here. So now, as the SWCC was already described, and the hydraulic conductivity function is important, and Professor Claudia will be describing how to evaluate the K values in her next lecture. So I will not describe very detailed about this, right? So I will just skip, in case if it is required I will come back whenever we have some time in the afternoons. So there are three things that we have to determine. One is soil water characteristic curve, RWRC, water retention curve, hydraulic conductivity function that Professor Claudia will be describing, and volumetric shrinkage curve. Right? Yesterday also there was a question in SWCC, some of the methods that were described, they mostly are like measuring or are estimating or controlling the suction, either total suction or matrix suction, right? And you also try to estimate the water content by weighing methods. How to get volumetric water content or SWCC, where most of the software take the inputs of soil water characteristic curve in terms of volumetric water content versus suction. So to do that, like a GeoStudio or Plaxis or anywhere, Plaxis recently it started taking. So to do that, we need to have a volumetric shrinkage curve, which describes the relation between theta and W. For this, dry density has to be estimated, volume, mass of solids per total volume. Volume is required here. So you evaluate the volumetric shrinkage curve also. You know that shrinkage which happens, so this is gravimetric water content, this is volume of the soil sample, right? So generally we draw like this, correct? We say that this is the shrinkage limit. Correct? This may be true for sandy soils or something, where you don't require the shrinkage, coarse grained soils. But actual curve varies something like this. What happened? Okay. So the actual curve describes something like this. So this is 1:1. This is how the slope. This is how the slope is changing. So the desaturation starts somewhere. The desaturation starts somewhere here, right? Constant volume happens somewhere here. So a huge difference in the water content range before it desaturates, before it starts, changing from the saturated conditions, and after it started becoming the unsaturated part, and before it becomes constant volume. So generally know that these 2 points are the same, right? But it doesn't happen. So there are a number of ways to evaluate the volumetric shrinkage curve, and water content anyways we estimate using gamma ray and time domain reflectometry, TDR, and these sensors we commonly use, and these sensors will be described today afternoon because we will be using them. They are very, very handy in using in the field. Quickly they can give the volumetric water content itself. So volumetric shrinkage curve, there are a number of ways to determine because we require the entire curve. Generally, mercury displacement is no longer in use. In international community, people don't use. Unfortunately, in Indian standard codes, still mercury displacement is still used, but then it is not used anywhere. Okay, so individual soil sample you take and then you immerse and do it, right? So that is no longer useful. We require the entire curve. For that, we use number of methods, maybe shrinkage box, but if you use highly expansive clays, it will curve, and determining the volume is very, very difficult. So simply by measuring the volume, width, etc. is not possible. So wax coating is one method we commonly use, because in the field also we use, right? Field sample has to be brought to the laboratory. We use a wax coating. So look at the consistency. At this consistency, definitely you can't do the wax coating, because it should have good consistency where you can hold the sample and coat it. You put it in a hot molten wax. For that you require good consistency. So you will be missing some points here. So somewhere here you will start, right? Hopefully that is before the desaturation starts. Otherwise you will be missing few points. And balloon method is one method which we also try to use, and which has some positive points, but it also deviated for some cases where you use a larger balloon volume is not considered, and also there is a air which is actually stuck here, and it requires a good contact between balloon and soil sample. Often that cannot be placed in the field, in the laboratory. So right, so we have also used clot tests where we started coating with respect to PVA glue, and therefore the glue, once it dries, it allows only air movement, and water will not go inside. So therefore if you immerse it directly in water to measure its change in the volume, water will not enter into the soil, so that soil will not get wet. After that, if you take it out and then keep it outside, it will get dried. So intermittently I can take the soil sample which is coated with PVA glue, I can put it in the water and measure its volume, take out and then keep it in the outside. So continuously water content will be decreasing, volume also will be decreasing. There is a thin film which is protecting water to enter into this. So we found that this is a very good method, and I think the comparison between different methods is shown towards the end, and these are some of the suction measurement methods. I think I will not mint up her time, so maybe in the afternoon we will have discussion around 2:30, and we will have around a half an hour discussion on these methods, and after that we will go to the field for measuring. Okay. So afternoon lab will be somewhere here only. We don't need to go to the lab. So if you have any questions, I'll take the questions, and these methods I will describe afternoon before we go for the field visit or field measurement. Any question? Yeah.
For care equipment, can we physically think of that the soil column is there which is fully saturated? If I am drying it, so I want to create a negative pressure which is equal to A so that water will dry off of soil. Is it like that?
Yes. If you are drying a soil mass, air should enter to your soil system or pore system. At what point it is able to enter is described by the air entry. Where exactly the desaturation starts.
And in case of say wetting it,
Actually, we call water entry, air entry, the different points are there. In a drying system, we call air entry. Okay, if you fully saturated system is there, and when you are drying the soil sample, where exactly air enters into the largest pore of the system. Largest pore of the system is called air entry value.
and water will enter in the smallest pore first if we are wetting.
Yes.
Yeah, you talked about hysteresis method, that in wetting and drying both the curve will be different. Now again I will re-wet it, the same curve. Will it be same or
It will be in between. So there is a loop which I showed. So you have a drying and wetting, right? So it will go in between. It will follow hysteresis, right? So it will be in between the loop. It's called secondary wetting, secondary drying, all these things are there.
similar to cyclic floating of the
Yes, yes, yes. Yeah.
The method-based saturation is done with the relative humidity method.
Hmm.
Sample absorbs the moisture that is
So
there.
can we use the microphone for the online people?
Yeah, true. You change the mic otherwise. Yeah.
So, concept.
take this.
So conceptually, can I use a small volume humidity chamber where I keep the dry sample and I set a humidity value? Where I directly know the humidity, and then after some duration I take out the sample and estimate the water content. So will I be able to plot the curve?
Yes.
So is it logical?
It is, of course. This is one of the methods we use.
Uh,
The vapor equilibrium method is exactly doing the same. Instead of using salts, you are controlling artificially using humidity chamber.
correct.
You are controlling the humidity at different points. So you set say 100, 100 RH or 99
95,
RH, then maybe 95, 96 RH or 90 RH, like that you are setting.
Correct.
And you are exposing the different soil samples to these RH conditions by maintaining constant temperatures, and at equilibrium you are measuring the weight. That is one of
Yes.
the methods we use.
Yes.
But now the question is, if you have expansive soils,
Hmm.
how do you control its volume? Because the volume also changes, right? If it is expansive soil, like you are going for a wetting path, then how do you do it? Like it may come out, or
Swell.
how the swelling takes place, and it takes very long time. These are very long time, very long duration process. Each method, for one particular RH, if you are controlling, it takes nearly months to come to equilibrium for one single point, right? So there are a number of methods they are available. In fact, we could estimate for compacted bentonates, powder bentonates also we did, compacted bentonates of different quality, where the specific surface area went up to nearly 600, 700 meter square per gram. For those clays in a compacted system up to 1.7 gram per centimeter cube dry density, we estimated the entire SWCC curves using different techniques, osmotic and vapor equilibrium, etc. Vapor equilibrium takes really time, long time. So lithium chloride, if you use around what 15 or 10 MPa, sorry 10 RH, I think I showed yesterday, right? K2SO4, lithium chloride, etc. So around 11 kilopascal, 11 RH or something, which can exhibit around 80 MPa or so. We went up to that.
Sir, and other question that I have, from the payment point of view, both the subgrade and granular layer. So even South African guidelines and MEPDG US based. So they mostly have like plastic deformation model. It takes into account of degree of saturation as a function. So if for an like it is not established for if it has to be done for Indian context, how should that a function of degree of saturation?
Degree of saturation is function of what?
Sorry, there is a like the equation follows a function of saturation. That model form is not
No, is it a modulus or what? What is it that which is function of saturation?
modulus. Yes.
Modulus, resilient modulus.
Right.
Okay, that she will be describing. I think
Okay.
she will be talking about it.
Okay.
Yeah.
We're gonna have a whole tutorial.
Yeah. That's it. Thank
Yeah.
you.
Anything else? I think there's a tea break. Huh. We'll have. Sorry. Yeah, please.
Drying and wetting, so why is that difference will be coming? What are the reasons?
First of all, the contact angle itself is hysteresis, which follows hysteresis. So during drying and wetting, you have different contact angles for soils. Okay, that is one reason. Another reason is capillary hysteresis. If you have a larger pore and smaller pore, which are both are connected, so the during raise it will stop here, and during drying it will be up to here. So that is the reason more water in the drying for the same suction and less water in the wetting. So this is a capillary hysteresis. It's called capillary. What is it? What is it called? Ink bottle hysteresis. Ink bottle hysteresis. So ink bottle, when you are trying to squeeze out the fluid from the capillary, so that time if you just leave it against the gravity, it stops at above the neck, right? But if you just try to take in the fluid, it will stop at here. That is because of the suction difference that is actually existing between two different pores. That most of the pore network within the soil mass is connected by number of different pores, right? So that is how it is described. So generally the contact angle varies within the soil mass. It can vary to even 60 degrees to even more than 90, depending on the wetting or drying conditions. So that's the reason the contact hysteresis is existing in SWCC, right? So we'll have a tea break, and tea is served outside in the lounge. So we'll come back and assemble here by 11:30.
We need the microphone for this. This was gonna be the record or something. Can I have, do I need this stuff outside? Yeah. Yeah, so it's gonna be tough. Okay. All righty. There's gonna be, please. It's very hard. Is that me or it's very hard? That's true. Oh, I see. I see. Okay, perfect. Should I try now?
You should come here. That's what we're saying.
All right. So I should stay here? No, I can move now. Okay. Can everybody hear me? All right. Yeah, I don't hear myself. Okay, so okay. All righty. All right. I guess still good morning for everyone online and everybody here. I'm just going to start a series of lectures on, like I mentioned that yesterday, about some of the concepts that we can just apply it to, well, transportation geotechniques, but also to every other, application that we have in geotechnical engineering, actually. So that's the fundamentals for that. And today we're going to be talking today, and the first lecture tomorrow we're going to be talking about sea pitch analysis and fluid flow, right? And for that, we promised this morning that we were going to get into the unsaturated conductivity function, right? Unsaturated conductivity function. So start making like this in here. So I just want to bring a little bit of introduction of the whole need. It's just basically for us to realize, and I probably am preaching to the choir right now in here because you all know that this is important, So when we have a saturated soil mechanics, usually it's been a success is because it was easily and widely implemented, okay? And that contribute to our engineering success all the time, okay? Practitioners found it to be easy to implement. And therefore, we just took the theory to be the only theory that was available and easy for us to do. For unsaturated soils, it's been a little bit more difficult. I was talking on the break with your Professor Bharat and about implementation, right? I've been trying for 20 years or so with my lectures and my involvement in the payment community to trying to get them into, away from the moisture content and a more fundamental constitutive models that include stress state variables like suction, right? And it's been a difficult thing, right? when people start talking about suction, you start getting, I don't understand the concept, right? Just talk to me about, and fine, we talk to them about volumetric water content or gravimetric water content, but we in our classroom, in our laboratories, we should be doing fundamental modeling based on suction, which is our, fundamental stress state variable, right? Why? Because, we are, there are many geotechnical challenges that are a function of unsaturated soil. Just to name few, the seepage and the flow through air dams is one of them. Volume changes from expansive soils, and actually this is how unsaturated soil mechanics started in engineering, right? We were only paying attention to expansive soils, and all of the conference available were conference for expansive soils. Thus, that was the only way that we talk about unsaturated soils and the moisture flow and the problems with, the volume change due to the moisture flow. Slope stability, we understand that under environmental changes, we do have big problems, right? This is one of the regions that we can just suffer that. Excavation stability issues is an unsaturated soil problem as well. Bearing capacity, if you have shallow foundations, usually you design a shallow foundation, preferably to be above groundwater table. It's an unsaturated condition, all right? Soil cover system and capillary barriers are very beautiful also, way to use unsaturated soil mechanics, because the soil barrier just serves as a they hold the water until it just start getting evaporated before it leaches down. And the performance of roads and railroad structures. Some of you are, how many of you are railroad engineers here? We have few here, 3, 4, 5, okay. This is, we actually make all these ballast to be on the unsaturated area, right? We never put this one underwater, all right? So it is a pure problem or a pure condition on unsaturated. And all of the concepts that you're gonna see here also apply for railroad conditions, okay? So the rate of flow is needed to solve most of these problems, the rate of flow. And this one is regulated to the hydraulic conductivity or coefficient of permeability of the soil. Okay, so how many of you are going to argue me that it's not the coefficient of permeability? Well, it is just a way of talking. It's funny because we talk about hydraulic conductivity, which is the right way to do. But when you graduate and you start talking to your boss, you talk about permeability, right? So I'm going to talk about permeability, because you're going to be talking about permeability. But I'm talking about not the intrinsic permeability, I'm talking about the hydraulic conductivity of the soil, all right? So that's the main concept on that. It's just a matter of talking to either practitioners or very pure, fundamental researchers. So, and this one is important not only when we have a steady state conditions, and we're going to go a little bit in here on that, and I'll be a little bit on there tomorrow more on that, but also transient flow or unsteady flow conditions through a porous media. So the water storage properties, I'm talking about the K and I call it K and SAT, the hydraulic conductivity function, right? Hydraulic conductivity function is important for both, but also if you have transient flow, not on a steady state, but if you have transient flow, you're going to need also the storage capacity of the storage properties of your soil, right? That is defined by the soil water characteristic curve, we're going to see later. So what I'm trying for you to learn is just to get interesting facts of the theory behind flow of water, the Darcy's law for unsaturated soils, how we use that, hydraulic conductivity concepts, and the estimation of the hydraulic conductivity. That's for practitioners, pretty much, And last but not least, for mostly on the research side of it, we talk a little bit about direct measurements and how we do that in the laboratory, right? So I'm going to try to do a little bit of everything. So flow, the state of the flow conditions can be a steady state. That means that, it's a long-term equilibrium analysis, and also the transient condition, right? And the transient means only time, right? That the changes with time. right? So all of these problems are water flow that are mostly transient flow conditions. Unless you're doing some stability analysis or a long term, that's how we design actually for a slope stability, is an equilibrium analysis, then we go for a steady state conditions. But most of the problems that we do have that are function of climate or environmental conditions are transient flow conditions, okay? So water flow is going to be regulated by the hydraulic conductivity, as I talked to you, and for both a steady state or transient flow, and also for the water storage capacity or the transient flow. So we have historically described water flow through saturated terms in terms of the hydraulic gradient. And I think Professor Bharat talked to you lengthily into this is the fundamental, okay, fundamental variable to figure out the sea pitch analysis. And it's important to us also to understand that hydraulic gradient should be also our fundamental parameter to explain sea pitch analysis. I'm going to tell you why. Well, I'm going to kind of go through different alternatives, you know, alternatives that we have used probably for instead of hydraulic gradient. Like, for example, okay, I can use volumetric water content, all right? If you say that the saltwater characteristic curve, you know, is related to the suction, you can convert it immediately to, you know, gradient, right? And the volumetric water content. But so that volumetric water content should not be used as a fundamental. Why? Because not always the flow of water will occur from places when you have high water content to places when you have lower content, okay? And this is another lengthy story there about thermal gradients, hydraulic gradients, and every single, you know, potential gradients due to different concentrations. So there is not always the water can flow from a region of lower content to a region of high water content. So this is not a good stuff to do, you know, to change, to get modeling through water movement. This approach doesn't account for hysteretic effects, the stress history variation, or any variation of soil properties, right? Another word that people have tried is the matrix suction. Matrix suction, not the hydraulic gradient, but just the matrix suction gradient. Well, flow of water does not exclusively depend, okay, on the matrix suction unless the air pressure gradient is 0, all right? So this is something that is important for you to understand. Matrix suction, and let's see if I can just do this. Okay, this one doesn't, it says, no, okay. So I can go here. So air and water, what happened is air and water is going to be flowing in the individual phases, okay? Not always going to be the two of them together. Not always going to have flow of vapor going in the same direction as the liquid water, okay? So if you can change, for example, different cases in here, we can have a case when we have air pressure, you know, difference in here, which is, you know, the first one is going to be less, more pressure than the second one. Same thing in here, more pressure for water and for this one, and you still have the matrix suction of 25, you know, port air minus port water pressure, right? Port air minus port water pressure. So if you have minus 25 minus 50, you're going to have a suction of 50 of 25. And if you have minus 50 to minus 100, you're going to have a suction of that. In this case, you will have less suction here, high suction here. So if we use this one as a gradient, the water is going to tend to, you know, supposedly, right, to go through to the point when you have higher suction, right? It's going to be trying to suck water from that point to this point. Look at, in this case, the air pressure is graded and the water pressure is graded. In the second case, you got in here graded port air pressure, but you got graded port water pressure in here, but then you still have the same suction value, all right, the same suction value. In this case, you got port water pressure, but the matrix suction gradient is going to be 0, all right? And you know that if you have port air pressure that are different and port water pressure that are different, you're going to have flow on both phases, you see. So this is just a little example, and the other one is the same thing. You know, you're going to have here more than here, the suction, so the water is going to tend to go through that way, and you still have vapor and water going in different directions, all right? So this is not because this is not a good idea as well, right? So that's why the hydraulic head gradient, I just want to show you a couple of examples, is important, and it should be the one that governs the flow of water in unsaturated salts at one. Together with the elevation gradient, of course, you know, we got the hydraulic head gradient. We're going to have also the gravitational gradient, and the velocity is usually much smaller compared to the other two. So we don't use it much on that unless, you know, you have evidence that the water is flowing out. So hydraulic head gradients can be applied to each fluid phase. Okay, this is the important part. Okay, so one thing is the flow of water going in this direction and the flow of vapor going in another direction, and it's a fundamental driving potential for flowing unsaturated in the soils we're going to have. And I hope I convince you of that. So the driving potential of water, you've been looking at in here, the flow of water can be expressed in terms of energy, and you guys are more on the energy side than I even do. So if you have any point, any elevation, you're going to have the energy due to the, you know, the elevation head. You're going to have one due to the port water pressure head, and you're going to have one to the velocity head, and the energy is going to be the summation of the three, right? You know these equations since your undergraduate school, right? And I hope you remember that, those undergraduate students in here. Okay, so this is what we have. So we got the driving potential can also be expressed if you just get the, you know, the unit weight of the water out of the equation by the potential of the hydraulic head, right? That's what we have. So we got gravitational head, we got the pressure head, and we got the velocity head, which is usually, again, negligible if you compare to the other two. So the total head can be expressed as the gravitational head plus pressure head. All right. So, and this is very simple way of estimating that, whether you have positive port water pressure or if you have negative port water pressure, right? If you have positive port water pressures, still it applies. You know, if you get a datum, you're going to have a gravitational head and a positive pressure head. And if you have a negative port water pressure, also you're going to have that both of them are going to apply. Okay. So how we use Darcy's law for unsaturated salts? Well, it can be expressed by Darcy's law, and you heard this morning about the Richards equation, and it's pretty much like I said. You know, I don't know who copied who, because I don't remember what Darcy's law was, you know, from that, but actually is the same concept, but I'm going to see the modification that we can do for the Darcy's law, right, to kind of reflect what Richards' equation is, pretty much, right? So we have the flow of water. We got the flow of water in here, which is, you know, proportional to the hydraulic head gradient in any direction, and the proportionality parameter is the coefficient of permeability of the hydraulic conductivity with respect to the water phase, right? So this coefficient of proportionality is what we call hydraulic conductivity, of coefficient of permeability. For saturated soils, this value is usually a constant value, okay? That's a constant value. Most of the cases, right? But that's not the case for unsaturated soils. For unsaturated soils, that coefficient, it has to be a variable, and you saw that this morning, of your suction value, right? Should be a function of your suction value. Okay. Oh, well, I have this one in here, but I'm going to have it. So basically what happens in here, because if we want to use Darcy's law, the K value cannot be a constant, okay? You can visualize, for example, what happens when you do have air into the soil. Remember, to have water flowing, you're going to have a continuous flow. Continuous flow. if you start getting into bubbles or discontinuous flow, like for example, bubbles of air is, they will not flow out, right? Or bubbles of water, if we can call them, it's just drops of water, will not flow. So you're going to need a continuous flow, or a continuous flow. But let's say you do have some air. Air cannot conduct water. You cannot get water through air. Okay, you cannot get water through air. So basically, they become kind of a non-conductive channels as well for water. And therefore, the air-filled pores that we got in here in an unsaturated soil can be considered similar to the solids that we got in the soil. Just imagine that we have solids in there, and therefore the flow of water are going to go just through the water, right? And basically, we can consider Darcy's law if we said, okay, these air pockets are like my solids, and now what I need to do is to reduce the water content, right? If we just reduce the water content, then we can use Darcy's law for that, right? So the coefficient of permeability with respect to the water phase is a measure of how quickly flow through a medium can occur, okay? And in this case, unsaturated soils. The different type of fluids will have generate different coefficient of permeability, but one thing is important for you to understand. The coefficient of permeability is not only a function of the property of the fluid, okay? It's also a function of the property of the medium that you do have in there, all right? So that's why we don't use the coefficient of the intrinsic permeability, which is, is related to the hydraulic conductivity by the gamma and divided by the viscosity, right? The dynamic viscosity of any fluid that you have in here, okay? So the coefficient of permeability in unsaturated salts is the variable that we will use, not the intrinsic permeability for you to do, okay? It's the one that has, the units of meters per second. Okay. So you also saw this morning from Professor Bharat that the coefficient of permeability is a function of, you can say it's a function of two of the three properties. It's a function of the degree of saturation and void ratio, or you can use the void ratio and water content, gravimetric water content, or you can use the water content and degree of saturation, okay? The coefficient of permeability in a saturated soil is a function of the void ratio. And you have that famous equation with the e to the cube, right? That you all know, okay? Nobody talk about water content, but the coefficient of permeability in an unsaturated soil is based on the void ratio, the degree of saturation, or the water content, okay? Water flow through the porous space filled with water. I hope I convince you of that, and therefore the percent of the voids filled with water is an important factor. So, amount of water content, okay? So some notes about this. The coefficient of permeability with respect to the water phase, and I always, remark this because there is another coefficient of permeability for the, for the vapor phase, right? There's another one for, for other phases, whatever you do have. You have a contaminant, for example, okay? So it will decrease very rapidly as the space of the water flow is reduced. So if your void ratio is reduced, this one is going to rapidly decrease. And not only that, the amount of water, because of you saw the little diagram, in the soil also increases the tortuosity of the flow, but and high percentage of the water in the pore space will be kind of bound. And therefore, an arithmetic decrease in the volume of water in the soil generally results in a logarithmic decrease in the coefficient of permeability. So you see orders of magnitude decrease in that one. Okay. This is to compare for different soils. This is to compare for different soils. For example, which of the, if you talk about saturated hydraulic conductivity, which one is higher? The saturated hydraulic conductivity of a clay or of a sand?
Depend upon the
Saturated.
sand.
Gonna be sand, excuse me. Saturated means oxygen zero. So So you got that. And what happens is if you compare both suction curves, right, both SWCCs or soil moisture retention curves, you're going to see that the water content, usually the porosity for a clay material, silty material is higher, right? If we talk about water content, you're going to have a little bit higher value there, and you get into the entry value and then you go down with the desaturation. For the sand, you're going to have probably less water content to start with, right? And then you do have yearly air entry value, like, we talked this morning also, the air entry value of sands are much less than the silts and the clays. And the desaturation rate occurs rather fast, all right? So if you just go down with with an equivalent graph for the coefficient of permeability for unsaturated soils, you're going to see that the saturated permeability for sand is much higher, right? It's going to start in here when it's saturated. For the clay, it's less than that. But what happens with the sand? That thing starts saturating rather fast, right? It goes down pretty fast. While if you do have the clay, it's going to try to get it when it reaches the air entry value, it's going to start desaturating rather slowly, okay? So obviously, the only way that we are going to have degrees of saturation, permeability for the sand less than the permeability for the clays is when we do have higher suction values, okay? Or lower degrees of saturation, like you said. Okay, this is important, right? Because it's a concept that that's a great answer, right? What is the coefficient of permeability? You say, well, it depends of the suction value that you're going to have, right? Whether it's higher or lower, and that's a very neat thing that we need to understand as well. So, what is the effect of saturation in the permeability? The change in water in void ratio is potentially small, okay, in soils of low compressibility, sand material, for example, and its effects on the coefficient of permeability will be also less, all right? Changes in the degree of saturation will produce also large changes in the coefficient of permeability, on the other hand. So it's often a singular function of the degree of saturation, right? Now, that doesn't mean that we have clay materials when we have high volume change, that we're going to need to correct that soil water characteristic curve for volume change, right? Because that's going to become an important factor, right? You're going to have a change in there. But usually the compressibility, okay, the compressibility change of the soil water characteristic curve is much smaller than the change due to the degree of the saturation that we got, okay? So that's very important. So, for the first time we do have that now the void ratio, the density is not as important, the change in the density as important as the change in moisture content of the soil. So the pore size distribution curve are usually used to predict the coefficient of permeabilities. And we talked this morning also about pore size distribution, right? When you get into the grain size distribution and you basically go into the soil water characteristic curve, basically what you're finding is a pore size distribution, right? It's like the negative of a photograph, right? It's a negative of a photograph. You got the grains, the grain size distribution, and now you get the negative, which is the pore size distribution, which is your soil water characteristic curve. And the same way, you can use the same thing to predict the coefficient of permeability. And I didn't bring the same scenario that Professor Bharat showing here for the grain size to the SWCC, but we have the same, summation of pore sizes that we can just go Childs and George method from the soil water characteristic curve to the hydraulic conductivity. But we're not going to get into that in here. We're going to get into other estimation more on the practical side of the profession. So the pore size distribution has also been used to estimate the rate of decrease with respect to saturation. Okay, so you are now familiar with the soil water characteristic curve. Okay, the permeability function, when you start getting into that, is going to need the soil water characteristic curve and you're going to need the saturated hydraulic conductivity. Those are things that I'm very sure now you saw the laboratory, hopefully some of you are going to go out, those in the field, and buy a saltwater characteristic curve device, right, and trying to just measure the SWCC or estimate it, and I'm going to show you some estimation methods as well, right? But if we have that one and a permeability value, we will be able to estimate the unsaturated hydraulic conductivity. Okay. So I'm talking about the 1950s and 1960s when Bourdin and Brooks and Corey suggested that the permeability function can be obtained by the saturated coefficient of permeability and the SWCC. All right. So we're not talking this. We're talking about 80 years ago, right? Not that much, but 60 to 80 years ago. So the soil, the soil is assumed to be incompressible for this, okay? And again, we can correct the SWCC for that. This is a very nice thing that we're not going to bring here. But what do you need from the saltwater characteristic curve? Well, you're going to need the air entry value. You're going to need the residual degree of saturation, which is in here when the volume, I'm going to show you in a minute, to estimate, the residual degree of saturation can be ready to estimate kind of a range in which the desaturation is going to occur. And the port side distribution index, that's how Brooks and Corey call it, but it's nothing but some parameter related to the slope of the saltwater characteristic curve. I'm going to show you in a minute. Okay. So residual degree of saturation, you already saw, is the value where the increase in matrix suction, previous slide, do not produce a major decrease in the degree of saturation. The second, the air entry value, is the matrix suction value that must be exceeded before the air start receding into the air port, and the effective degree of saturation for points within the air entry value and the residual value can be estimated by an equation, okay, which is going to be a function of the air entry value divided by any suction value that you have in the curve or in that range from here to here before the residual to a lambda parameter. And this one again is for suction greater than entry value. That lambda parameter is related to, this one is the, here we go. This is the lambda parameter here, the slope of the saltwater characteristic curve, right? And they propose this equation in which the lambda is related to the delta parameter, and then the delta is putting here in a power equation with the degree of saturation to estimate the permeability at any one of those points. Okay, I mean, this is a way for you to save a lot of time and money, right? To estimate the permeability function. So this one is a prediction. I'm going to talk a little bit more later on that prediction, but this one is one of the ways that the profession has done it. And I'm emphasizing always that there is nothing like laboratory testing, and you know that. There's nothing like laboratory or field testing, if we can do that. But because you want to implement some of these theories in your profession, okay, or in your projects, I think you can start with something on the predicted side, always taking into account that you're going to have a lot of variability associated with the prediction, right? Uncertainty. So you need to count for that uncertainty because you are doing a prediction. So I'm not advocating for prediction, but I'm saying these are useful if you want to implement, okay? Delta and lambda values are also suggested for different everything okay? All right. So delta and alpha values are also suggested for uniform sands, salts and porous rock, natural sand deposits. But again, if you do have a saltwater characteristic curve, whether you predict or whether you measure that in the laboratory, you can estimate your delta and lambda parameters, right? So the closed form solution becomes, if this is the degree of saturation, you change the delta for the value, and it's lambda over delta, delta over, just come back in. The math is good, so you just can go for that. And then the permeability becomes that closed form solution equation, right? So this one is an important way, an important. What?
Just hold for a second.
Yeah.
I think an online participant are not able to see the equations.
They cannot see the
Yeah,
equation.
just
Huh.
they're fixing it now.
Okay.
Let's see.
Is well, the material will be available, but yeah. And
Ask whether they're able to see one. No. Can you just ask? No. Okay, fine. Please go ahead.
okay.
I think they're able to see.
Oh, it's just the video lagging and some internet connection
Yeah,
probably
yeah.
problem.
Now they are able to see.
All right.
Please proceed.
Let's keep going then. All right, so this is one of the methods, but I brought a couple of more methods in here for estimating or predicting the hydraulic conductivity function. And those are usually empirical or semi-empirical values that you're having here for that. And it's and they're being derived from the matrix suction versus degree of saturation curve, okay, as opposed to the matrix suction versus water content or volumetric water content, the saltwater characteristic curve, right? So all these procedures are essentially obtaining the permeability, make use of the saltwater characteristic curve in the degree of saturation form, volumetric form as well, and basically is the pore size distribution form that is the basis for the prediction of the permeability. So I got three here that are important. For this one is already the Gardner equation. This is already, that's the Brooks and Corey equation. And again, this is from different source, but it's the same parameters. This one is another one that works, when it has A and N constant. I'm going to go in for that in a minute. And there's another one that has in here an N prime constant. But most of them, even if they are, are pretty much of the same form. And it's been working, I'm talking about 70 years, people working with that. You know that the petroleum engineering has been using that one way ahead of us. Okay, they're using all this with no problem. Gardner equation, this is the second one that you saw on the list, that has an A and N parameter. And it's very interesting. Gardner is, you saw some of the SWCC models, right? You can use Fredland and see Van Genogten is Van Genogten and all the students, Moalem, Bourdin, all of them are great equations. Gardner is another great equation. The nice thing about Gardner, which I don't like it, but is, it was nice at that point, is basically that is a, kind of a function that requires only two parameters. And for those that do modeling, right, it's easy that not to get into getting into the infinity or getting into very unstable programs. When you start getting into 3, 4, 5 parameters, that thing can start making a lot of roots and start making a lot of problems when you model, right? So this one is an easy one to model. A is a function of the air entry value. And I said it's not the air entry value, it's a function of the air entry value, right? And the N value is supposed to be related to the slope of the saltwater characteristic curve. Although we have done some analysis with that, and sometimes I can see that the N value doesn't appear to be the one from the saltwater characteristic curve. So in other words, what you do is you just go, see if I have a little bit of space in here. I guess I don't need this. I can use my finger, but for example, if you do have your saltwater characteristic curve, right, and you got several points measured in the lab by any of the methods that you learned yesterday, right? I'm talking about in here your volumetric water content or degree of saturation and your suction value. Let me call it pore air minus pore water pressure, and you got all these points. And then you do a solver or regression analysis, nonlinear regression analysis, you input your porosity there, or if it's the degree of saturation here is 1, and then you just, put a function to that, right? And in order to do that, you're going to need fitting parameters, right? The fitting parameters for Gardner equation are A and N. For Van Genogten and A, N, and M, so 3 parameters. So if you get into the Freeland and C, you're going to find 4 parameters, A, B, C, and H sub R, okay? So these are nothing but fitting parameters to the data that you obtain in the field or in the laboratory, right? So this is how you obtain these parameters. You measure the data points, okay? You go to solver, you just put, the sum of the square errors to be a minimizing error in there, and then you put any equation you want, right? That the right-hand side of the equation minus the left-hand side should be, 0 or minimize it, and basically you find those parameters, right? It's a little bit probably, high for our, undergraduate students here, but you eventually will gonna do that, right? So that's how you obtain those parameters, and those parameters are the important ones because they are the ones that you're going to use and need for the prediction of the K and SAT function. This one is the Van Genogten and Moalen model that I'm now talking about the 80s. And again, you got the K SAT value here. You got your suction value here. Okay? And then you have 3 parameters, alpha, N, and M, that you obtain in the same way. Those are constant, make out of your relationship, and then you use them directly from your saltwater characteristic curve to get your K and SAT function, all right? So these ones are more continuous. Gardner is pretty bad, Gardner, the problem is Gardner will keep going like that, through zeros and negative values if you keep going. So just be careful with Gardner, right? For a small range of values will be fine, but not for all of it. Van Genogten are great equations. The only problem with Van Genogten's equations are, that if you are modeling, this guy probably can just get a residual value and flatten down. And then if you have low water contents, you get into infinite values, right? And then you start getting into trouble for that, right? Freeland and Sink equation, on the other hand, is something that you just get that one and just get, into that here. That creates some problems as well, right? It's not a lot of more instability because you need 4 parameters. But it fits the equation to the 1,000 megapascal or 1 million kilopascal that we talked this morning as well. And this is good for the modeling effects, right? So I like that one because of that, if you are modeling. If not, Van Genogten equations are very good, right? Unless you do have a residual condition that is, you don't have enough points, and then the residual condition is going to flatten out pretty quickly for you, right? So this is all. You need to try different models to see which one will work best for you. This is another one, Van Genogten et al. Also, and this one is, again, this one will require the volumetric water content at saturation, the residual volumetric water content in here, and it has a parameter, the famous P parameters. We spent a lot of years trying to figure out the P value for this equation, and they have an M value here, which is a constant, which is assumed to be 1 over n, and this one is from the saltwater characteristic curve. This P value is a constant that describes the degree of connectivity. So between the water conducting pores, some authors have talked about that this depending on the contact angle, some about the tortuosity of that. So there are many theories about that, but this is the parameter that if you change, the whole thing is going to change, right? So that's, that's the holy grail of this equation. It's not easy to that. So, but nevertheless, it's another way. But again, we need more, how to associate this one to the material properties. It's not easy. Okay. We also talk about hysteresis. If the saltwater characteristic curve that you're using to estimate the K and SAT function has hysteresis, therefore you will expect the conductivity function to also have hysteresis, right? And the coefficient of, so you're going to have in here, this is your salt water characteristic curve, the drying going down and the wetting. There you're going to expect, or you're going to be measuring that the permeability here is going to be the drying and the wetting. Also, you're going to have hysteresis. Okay. When you have volumetric water contents, I don't know if I have it here due to the direct, due to the direct relationship between the volumetric water content, between the suction and the volumetric water content, actually, if you plotted volumetric water content and the permeability coefficient displays no hysteresis effect. It's not that there is no hysteresis, it's just there is no plot, there is no difference in that. And you find this one. So you be very careful with that. The two curves actually go one on top of the other one. What we do, so I don't know, we didn't go through that, but what we usually measure in the lab is easy, but you can do either way. You can measure the drying curve, right? It's easy to put a high suction value, saturated sample, and then you start applying potted pressure or just changing your suction until you get into the drying side of the tank. It's an easy thing to do. There are methods also to estimate or predict the hysteresis effect depending on the soil that you got. I think Pham, one of the students from Professor Fredland, had a very nice couple of papers, or he worked 2 or 3 years on that, when he estimated that the hysteresis might be about half log cycle for sands, about I think it was 1/4 of log cycle for sands, half cycle for silts, and about 1 cycle for clays. Okay, and he demonstrated that with obviously a lot of data. A lot of good data demonstrated that. So you can do is measure the drying curve in the lab, right? If you don't have, now if you have time, you can just go for the wetting curve and do the hysteresis right now, right? And but if you don't have that one, you can actually predict the wetting curve, or you can measure the wetting curve and predict the drying curve, whatever you want to do. But I mean, there are ways to figure out the hysteresis of the permeability if you have the hysteresis of the saltwater characteristic curve. And again, I've been very practical in here, on that side of that. This is the effect of the anisotropy on the permeability function. Again, if you do have usually any deposited layer system or any deposits of one layer, right? Usually you're going to have, what's going to be the permeability, if you're taking the anisotropy, the permeability in the horizontal direction and the permeability in the vertical direction are going to be different, right? It's deposited. Which one is higher? X, right? X 5 to 10 times, 15 times more than the vertical. So that's another thing that for modeling is very interesting, right? We include anisotropy. Actually, the results are way different to what we do. We've just put, we always assume isotropic conditions, right? Big mistake if we're trying to do something in the field. But it's, less time consuming, and we just go for that. If we got something like that, the permeability on the horizontal direction is higher and the permeability on the vertical direction. And therefore, you should expect that there is also a difference between the two unsaturated hydraulic conductivity functions. Do you guys have any questions on that? I don't mind stopping in the middle, and then I'm going to continue with the measuring one. All right. Yeah? Yes?
While explaining VZ molem, while explaining VZ molem hydraulic conductivity function, you mentioned alpha as something related to diffusivity coefficient. But if I am not wrong, it is something related to air entry suction, right? Inverse of air entry suction, if I am not
wrong.
Air
entry value?
Yes, ma'am.
Oh, you're talking about the...
Yeah, I don't remember the slide name, but yeah.
You're talking about the lambda value that...
VZ molem, Van Jenissen molem,
the Van
hydraulic
Jenissen
conductivity
model.
function.
Okay. This guy?
Yeah.
this guy alpha.
Yes.
Okay, and again, I'm a little bit of critical about that, but yeah, it could be. You know, it depends on if you use the degree of saturation, volumetric water content, gravimetric water content, okay? For one of those functions, you can relate this one with the air entry value directly. And you said it's 1 over air entry value, right? That's what you
Yes.
said. Okay. And this is okay in one of the functions that we get. But when you start changing the scales and normalizing it to different things, this sometimes may not apply. So you be very careful of that. So it is related to, I like to say that, but it doesn't mean that are exactly being able to measure. Okay. So that's what I think it is. And I don't remember which one of the two functions are the one that you can do that, but the other ones are, you know, perhaps not as, you know, that. The thing is, we read this one, we go through the literature, and then we just put the air entry value there, and sometimes it doesn't work. It doesn't work.
I think he's pointing out that it's written diffusion coefficient, constant.
Yeah.
Alpha, it's written in the text.
Oh, diffusion coefficient
Yes.
constant. Okay, I see what it means. Yeah, yeah. So it is related to the air entry value. Mhm.
Yeah, that's
Yeah.
what.
It is related to the air entry value.
Yeah, it's
I'm
something,
sorry about that.
the units something 1 hour kp or 1 hour meter something.
Yeah,
Yeah.
something like that. Yeah, that's true. You're absolutely right. So this one is not. All right, any more questions? Okay, good. All right. So direct measurements, right? Direct measurements in here. So now, there are different methods that we can do. Like, you know, this is now more into the research side of the question, right? There are two methods that to measure the hydraulic conductivity in the lab or in the field. And there are direct measurements. The permeameter is one of them. The field measurements also use kind of permeability tests to do that. It's a little bit more expensive, but can be done also in the field. But the problem obviously is that the measurements of the permeability have to be done at different moisture content values, right? Because we need the whole function on that. So laboratory tests are more economical than the field tests, because, you know, field tests are more difficult for you to control where the water is going, and, you know, just to being able to collect the water, and you know that, okay, this one represents this amount of moisture content in the soil is more difficult. Laboratory gets more economic and more easily to control. There are different procedures to measure the permeability. You can do it in terms of the pore water pressure. You can do it in terms of water content. And again, I bring this over also because we use that all the time. Even if we know that the water content is not the fundamental variable that we need to do, but we do that all the time. And what we do now that you know that, you know, even if you can go for pore water pressure measurements, because the high suction values, for example, in the field, you're going to need a high tensiometer, a high suction tensiometer, which are very expensive. If you have low sandy material, you're going to be able to get tensiometers that are much cheaper on that. But if you cannot measure pore water pressure, then you're going to need to measure water contents, right? And if you measure water contents, then you go to the saltwater characteristic curve and you just go back and forth, right? Go back and forth. And then you can do a more fundamental analysis with the suction value. Okay. All the methods use, again, the Darcy's law of validity. The flow rate and the hydraulic gradient are the variables usually measured during the permeameter test, same way that you learn in your undergraduate school for saturated conditions. The steady state is a flow rate, and the flow rate and the hydraulic head are kept constant. For the transient flow condition, the flow rate and the hydraulic head vary with time. Okay. The steady state method is used usually for undisturbed and compacted samples. You can use any of the two. There is always, when you talk about a steady state, you leave a constant head on an unsaturated soil element. And I'm going to show you in a graph, but I like to summarize before I get the graph in there. And then the matrix suction and water content of the soil are maintained constant. And that's the important part of it, okay? And then when the Q in is equal to the Q out, the hydraulic conductivity is calculated for a particular water content that you got in the soil, all right? So it's the same thing, you just need to change the water contents of the soil. The procedure is repeated for different suction or water content values. The procedure starts with usually saturated conditions, and then you start drying the samples until you get less water contents and different points in that. And the water content must be measured after each stage, which is a problem sometimes, right? Because you're going to need probably different samples, right? You're going to have a sample that you're going to be putting in here, right? And then you're going to put it at a particular suction value or water content, okay? Let's say you're going to control the suction because you do have the time, you have the apparatus. So basically to do that, you're going to need to put high air entry stones at the top and at the bottom of your sample, all right? I'm very sure you saw them yesterday in the lab, okay? And then you're going to remember that the suction is pore air minus pore water pressure, right? So basically what we do is we control the pore air pressure and then we measure the pore water pressure, all right? We control. How do you control it? Well, you control with a particular air pressure supplied. When you can measure with a manometer, you can measure what is the head of your, that you are imposing in there. And then you can put some tensiometers in here and measure, in a couple of points, the head that you're going to have in there and use the average of those two to imply a head for the whole sample that you're going to have in there. So the coefficient of permeability will be basically the average, correspond to the average matrix suction in the soil. And we calculated, if you use the Darcy's law, it's going to be calculated, you solve for K, and it's going to be the flow of the water, the area of the sample, the time it takes, and this is the pore air pressure, that's the pore water pressure, and you use the average value for those 2 points that you put in here, okay? This is the head already, and basically you get pore air minus pore water pressure, and you get the equation for those 2. So this is the way that we calculate the steady state condition in the laboratory, right? So there are limitations, obviously, for that method. It's very difficult to start getting flow out when you have very low water contents. I mean, you can try it, but it's absolutely difficult. You need to avoid evaporation rates. You need to know a lot of problems that are related to the laboratory field. So high matrix suctions are difficult to measure. We are limited by the air entry value of the ceramics, so you're going to need different ceramic stone depending on the soil. If you have a sand, probably 100 kilopascal will be fine, or the 1 bar stone. But if you have a clay, you are limited to 15 bars. I think this is the maximum I can get, 15 bar ceramic stone, which is 1,500 kilopascals. What if you want drier than that? It's going to be difficult, right? Water flow is very low, so it's going to take a long time. We're going to take 3 PhD students to measure something, and we don't want that, right? We want you to graduate and get out of here and get a job. So basically, and this air diffusion of water, and all of these problems that might happen when that those specimens are put in a laboratory. And also, you're going to have some shrink. It's going to be volume change when you start lowering the water content of your sample, and now you start getting the sample detached from the air entry stone. You're not going to have flow, continuous flow, and so forth. So it's kind of difficult. So we got the transient method, and I'm going to bring in here I guess one that at least I've been successful trying to getting data out of it, and it's basically the instantaneous profile method that Richards and Weeks proposed in the 50s, right? And again, here is the summary. It's a transient flow method. The method used a cylindrical specimen. Basically, you do have column, and you just put that column in the horizontal direction. Why? To avoid the gravitational, gradient. You just want the suction gradient going on in there. The flow can be a wetting or a drying process, like we were mentioned this morning. You can apply pressure on one side and let it dry, or you can open one side and just let it dry, or so forth. So it can be depending on the way the water is introduced to the specimen. The variations, you can measure the water content, and basically we're going to be talking about the moisture sensors. We use the same moisture sensors in there, where we can just basically install them in the sample, right? Those are the sensors right there, and basically you can measure the water content in there. And you can measure pore water pressures also independently and figure out your whole saltwater characteristic curve. Usually it's difficult to put many sensors in a column, right? Many sensors. So and you want to do a column that you don't want this to be a huge, because you don't want the flow going up and down on the horizontal direction, okay? Because you're going to need to estimate the amount of time that it takes the water to go from this point to the next point. We're going to see that in a minute. And if that thing has a lot of tortuosity, it's going to be tough. So you can measure only the water content and then get the saltwater characteristic curve and get the suction, or you can record the pore water pressures and then determine the water content from the saltwater characteristic curve. So again, you can go back and forth with that. Usually these are confined in an impervious tube that is set in a horizontal position. Suctions are measured at different locations along the length of the tube. The pore pressure is maintained at a value, usually the atmospheric pressure, and water flow is introduced for one of the ends. So how do you introduce that? And I think I'm running out of time, right? Am I okay? This one is run out of battery. 12:30?
No.
So, okay, so I'm almost running out. So I'm going to just wrap it up in a second. Sorry about that. So the suction measurements are taken as a function of time, and measurements are taken until the water has advanced through the samples. So this one is important, right? The time. Okay. So you got that tubing here, and basically this is what we did. We got this one, and we had actually made a space for just get tubes in there and get water contents out of that, and then pack it again with the same water content. Is not easy, because then you have to wait until everything equilibrates again, but it was doable. And basically what we did is we put, soil in here that was higher water content, and soil in here that was open on this side. Soil in here that was less water content, right? Or we just put in here everything saturated or just very high water content, and just open one end and just let the water to get out by evaporation. And in Arizona it's very easy to get that evaporation going on, so there's not a problem on that, right? If you have in here difficulties to get evaporation because you have a relative humidity, then you're probably going to be able to induce some pore pressure, right? Or some air dryer, hair dryer stuff or something that you just dry the soil on one end, right? So that's what you get on this one. Right? And basically you install inside all the sensors that you measure the water content with time. And we put this one for about a year or so, year and a half. I got one of the students working on that, and he was able to get not only for, you can see here that we just were putting material at different moisture content, for example, to figure out different ranges, because when you put one water content, then you are subjected to have, to wait a lot of time for this one. But if you start from different water contents, then it's going to be able to have more points on the K and SAT function, right? So this one is the work that one of my students did in Jacqueline to determine this one, and not only for samples that were intact, but we also did some cracked samples, because we wanted to figure out how the water content will behave around the cracked material. We were working on some of these unsaturated soil problems, all right? So The air entry value and the residual suctions were estimated from the saltwater characteristic curve. This one is a lower value that we have for the permeability function in here. And is, there are a couple of theories, but basically you just can go low forever, right? There is a point when the vapor start gaining the gain over the liquid, right? And basically Ebrahimi and Birang estimates that the lowest permeability before you start getting into the vapor phase is 10 to the minus 14 meters per second. So if you see everything on the literature that we do have, I limit this one, whatever values are, we limit it to the 10 to the minus 14. But depending if you have some value here. So you do have the K-SAT is easy to calculate for every sol. You know how to do that. We calculate the permeability between the air entry value and the residual condition, and we limit the value to the lowest value, which is 10 to the minus 14. And basically, this is how we put, you measure water contents in here at time equals 0, and the suction value, if you have, sensors for that. And after a time, and I'm talking about, you can do that one as many times, actually we put something to record it, right? And basically you measure the water contents at another time, so you do have the time. You have the space between this one, where the water is flowing out, and with this data, you just use Darcy's law, and you calculate the equation from Darcy's law, and basically what you're going to need in here is the hydraulic gradient between those points. We use average values, like, average suction for that. And basically, yeah, that's the equation we use. This is the change in the volume of water between the 2 points. You have water content measurements, right? So you can calculate that. We got the cross-sectional area, the change in time, and the hydraulic gradients. And this one is calculated by the amount of water. It's just basically the summation or the integration between those two points, right? Is the difference between the 2 points and the difference in water contents in and out. So this is how you calculate the change in volume of water. And the hydraulic gradient is also determined by this equation, when the hydraulic gradient in here, the head, is the average of the two suction values that you have. Okay. How do you get those suction values? Again, you put sensors in there to measure the suction, or you go directly to the saltwater characteristic curve and obtain the suctions out of that water contents that you have. And that's how we calculate the hydraulic gradient. These are the points we were able to get. This is one sample that we got only for saturated conditions. Then we start playing with different saturation in here, and we were able to do that. Variability will exist not only in the SWCC, but also on the K and SAT functions. And but we were able to get very close to the function that we wanted. Okay. The disadvantage is time consuming. The proper flow rate is very difficult to get. If the flow rate, if you're applying, some flow, the flow rate, probably recommended values between 0.2 to 5 centimeters cubic per day, but it's difficult to choose that. If it's too high or too low, it's going to be tough. If it's too high, you're not going to be able to measure the changes. If it's too low, it's going to be crazy. And actually, the accuracy of the test is a function of the space that you have between those 2 points, right? If you do have the space too high and the times too high, there's going to be, the water can go anywhere, right? And you can have more inaccurate results. All right, so almost there. I'm sorry, I'm over your time in here, but you guys have any questions on that one? There is another method of estimating the K and SAT function based on also the pore size distribution analysis. I'm going to get the material for you guys, to get to that one. But I wanted to bring a little bit more practical oriented equations here. Any questions that you got? All right. It was clear, or you didn't understand anything? What was that? All right. Thank you very much. So what is next?
Lunch.
Lunch. Okay, so I was just between you and lunch. Trouble. Oh, any questions from online? I'm sorry. Well, it seems like there are no questions online. Right.
Yes, sir, it's
Yes,
audible.
audible.
Am I audible?
Can you hear Professor Bharat?
Am I audible?
Very lightly audible.
अभी सुनाई दे रहे हैं? Is it audible? Or still is it feeble?
Online participants, is it audible now? Exer's voice, is it audible?
Bharat sir's voice is very lightly audible to us.
Oh, it's not audible, it seems. Very feeble. उनको सुनाई नहीं दे रहे ठीक से. इधर का ना? इधर का नहीं, ऑनलाइन में. Is it fine now?
Yes, sir, it is fine now.
Okay, thank you. Okay, any questions? I'll start the presentation in 5 minutes. There is a small technical glitch, but do you have any questions? What we couldn't discuss during the break, you can ask now. At least few things I can discuss. Yesterday the hanging column method was shown in the laboratory. Hanging column method or negative column method. Although the setup appeared to be slightly different, but it is a wonderful method to evaluate the suction values at low suction values, especially good for sands or something else. So what is the principle behind this? For example, if you have a funnel or something, a container which contains soil in it, right, on the right hand side there is a soil, and if it is connected to a water reservoir, so there is a water reservoir that is connected to the soil. It could be a column or it could be a small container containing soil. Now water is in direct contact with the soil, so what is expected? Water would raise to this level, right? Is it there? Just, yeah, sure. Yes, sir. Just a second. You can directly open, it's fine. Okay, sorry. Sure. Thank you. If this is connected, soil is connected directly with water, and you expect that the water level would be here, correct? So soil will be completely saturated. What if I raise this part? What is expected? And what if we leave this particular part, if it is hanging? Would the water dip and soil will become fully dry? if you are raising continuously, then what happens? So the level would be here, but it would go somewhere here, right? If this is taken to here, then what will happen? The level is only here, water level is only here. So would there be any water here?
Some part also spread. Negative pressure. Due to capillarity, it spread negative pressure.
In fact, fully water will be present. If the soil is, if soil air entry value is more than this particular head difference what you are seeing, then definitely water will be there. There will not be any discontinuity. So this water will be available against the gravity. That is what, no, if you take clay soil, fully saturated, water will not deport. You take from consolidation, after consolidation, soil is fully saturated. You take out the soil, hold it, water will not deport. It happens in sand because sand, the suction or soil water potential is less than the gravity force, right? Finer and finer, it will be able to hold the water. That is the tension we are talking about, right? So that is the method what we are trying to use in hanging column method. So therefore, a large column with compacted with sand or any soil which is compacted and connect to a reservoir. This is the reservoir, this is the reservoir, this is a sand column. Now water is expected to be up to here, wherever the water level in the reservoir. Above this, you may have some capillary, and after that the water current would be decreasing. So at any distance from this level, this particular level, say if it is 1 meter, a 10 kilopascal suction would be there. I can measure the water content correspondingly, correct? Above the water level, that is a negative pressure only within the soil, correct? So that way I can establish the soil water characteristic of simply for sandy soils using hanging column method or negative column method, correct? So but this is suitable only for such soils because by 2 meters if you have a column, that itself is difficult. So that means within 20 kilopascal entire SWC should be established, correct? If it is 20, should have this. If 20 is somewhere here, then it is not useful because you will have only these points, right? So in sandy soils, as the air entry value is nearly around 2 kilopascal or so, this will be useful, very useful method to evaluate the SWCC in the laboratory, okay? So generally we placed volumetric water content sensors like what I showed in the morning. So those sensors based on resistivity and other things they work, and generally they are related to dielectric constant. So dielectric constant of the media. For water the dielectric constant is 80.4, for air it's 1. So in between, partially saturated, based on the dielectric constant it directly gives you the reading of volumetric water content. So that's the concept we use. So based on those sensors we will place at different points. Now we can raise or decrease this level so that we established hysteresis, drying, wetting behavior for several soils, coarse soils, right? This will be a good method to establish that. Tensiometer, yesterday also there were a lot of questions. Tensiometer, very old method. In soil science this has been used in since time immemorial, because for the crop growth etc., people measure suction values. The suction should be less than the wilting point, otherwise plants die. So the tensiometer, amazingly, it works with a principle called using the concept of air entry value. So you have a higher entry disc. This is something like a higher entry ceramic disc. So it's just like a porous stone, but it has a finer pores than your porous stone. Porous stone, which you use it for the odometer or consolimeters, so it's finer than that. How fine it could be? It can be as fine as 1.7 into 10 power minus 3 mm. That will give a air entry value of 1 bar. 1 bar is 100 kilopascal. Imagine if you want to go for 15 bar, 1500 kilopascal. The size should be in the range of 10 power minus 4 mm. Very fine. Beyond that we can't reduce. As some Bhargav was asking in the previous class, can we design something, small pipes, etc. This itself is very tough. But soils have much higher suction or thinner pores, finer pores than the ceramic disc what we can design. Maximum capacity is 15 bar, that's it. Beyond that I haven't seen. Commercially available air entry discs, maximum capacity is 15 bar, 1500 kilopascal, right? So essentially it has pores, pore size is defined, very well defined, uniform pores it has. Now if this disc is placed here at the sensor tip for the tensiometer, and this is fully saturated because this entire column is fully saturated, right? You need to saturate the tensiometer before placing it in the for the measurement. This is fully saturated and disc is here. If it gets fully saturated, this side, this is a water column. This is water column, this is soil. So in between what you have is ceramic disc with tiny pores. Pores are filled with water. Now this is acting as an interface between soil and water reservoir. So what is expected? Here the potential is low, here potential is 0. What is expected? Water should move out, correct? Water should move out. But if I tightly close this reservoir, water reservoir, can the water go out? Water can't go out unless until this is replaced by air, correct? It has to be replaced by air. Then air has to come from soil only, because there is no other way. From only air there is a passage, but whether this ceramic disc could allow air to enter, it depends on the air entry value of the ceramic disc. If the pore size is 10 power minus 1.7 into 10 power minus 3 mm, which exerts a 100 bar, which has an air entry value of 1 bar, which is 100 kilopascal. If the soil has a suction of 80 kilopascal, right? So air cannot enter. Air is restricted. Then what it does? It tries to exert pressure for taking the water. So this negative pressure is transmitted to the water column. That is measured in a gauge, which is given as 80 kilopascal. That is how tensiometer works. So clear, right? Water cannot come out, but air cannot enter. That is the situation you are creating. So therefore the negative pressure is transmitted to the water column, right? It is in tension. Just like a capillary is placed in a reservoir, there is a negative, water raises, completely saturated, but there is a negative pressure. Exactly the same situation you are creating here, right? So, but it has some limitations. Limitation is, this is something like this very old type. If you try to purchase in market here, local market, for even 5,000, 2,000, 3,000 also you get tensiometers, old type, which has a pressure gauge, etc. But it will not last for long. Now you have digitized ones, digitized readings you will get directly, T8 tensiometers, etc. This is what we are trying to use, and directly the data can be collected, which can be connected to data logger and which saves the data. You can also set the interval so that it can save the data for you. how often you want to record, right? So which has certain limitation. Limitation is not coming from the air entry ceramic disc. Disc I can improve to 15 bar, like 1500 kilopascal, but it can't measure beyond 100 kilopascal. Okay, so limitation is coming from here. So this porous ceramic disc, when the soil suction is say 1500 kilopascal, when I just try to place it, what is expected? The negative pressure is transmitted to the water column, right? So if the soil has a negative pressure of say 150 kilopascal, what does it mean? With respect to atmospheric pressure 101.325 kilopascal, around 40-50 kilopascal is less in the water. So we have concept of vapor pressure we heard in the previous class yesterday maybe. So if the vapor pressure is falling below the saturated vapor pressure, cavitation takes place. Cavities form here, bubbles will form. So we saw the phase diagram, right? Yeah, we have a phase diagram, right? So here at the same temperature, either by increasing the temperature, you can change the phase from water to vapor, or by reducing the pressure. At the same temperature, if you decrease the pressure of the water, phase transfer will take place. If it comes down below the vapor pressure, around 3.515 or something, what we estimated yesterday at room temperature, if it comes below that, cavitation takes place. The same phenomena what we experience in triaxial systems, saturated triaxial systems, when they are heavily compacted, when you are doing a undrained test, this happens. Okay, if the back pressure is low, then this can happen. Okay, because if you remember, it has a tendency to expand if it is a drain test. In undrained test, it can't expand, but pressure drops, it goes to negative, right? This is shear strain, this one, you remember this kind of a curve, it goes to negative. If this negative value is large, then cavitation takes place. That's why you need to increase the back pressure. Higher back pressure, you need to conduct the test in CU. Okay, same thing happens. So this has a limitation that it can't detect or measure the suction values beyond 100 kilopascal minus vapor pressure. Okay, so this is 100 kilopascal or 101.325 in Guwahati. If you are measuring in somewhere in Arunachal Pradesh up, what will happen? Atmospheric pressure itself drops to 80 or something. Your measuring range also drops. So then you can only measure maximum value up to 75 or something. Beyond that you can't measure, right? So we have done a lot of tests. Not just that, even for sands, even for sandy soils. If you use tensiometer, the equilibration that is required to establish the negative pressure within the water column is large. So forget about clays, silts, etc. This is a Brahmaputra sand, and either one is just simply, taken a soil in a cover polythene bag and then place the tensiometer, and then we were trying to measure readings. Second, in a compacted state, we were doing this. You see, for certain conditions it takes even 2 days to get one reading. Equilibration time is very large. This is for Brahmaputra sand, almost like a uniform sand, uniform fine sand. So imagine what happens with silts or something else. So you cannot get an instantaneous reading using this particular method. So the difference which comes is this: For the drying and wetting path, this is the equilibrium values. We waited for nearly, the test itself was conducted for one drying path nearly 30 days or so, more than that. And this is what we got, and this is for instantaneous method. What you want to do? Just put the soil and connect with the reservoir, just let it pond, and connect one tensiometer, another water sensor, water content sensor. Instantaneously it starts giving reading, That's what many are doing, it's not correct. So therefore, I don't recommend to use suction sensors in the field. You should have established SWCs in the laboratory for a representative soil sample, then measure the water content. Water content, it's a very quick method. Immediately it gives the reading. The variability associated with the atmospheric conditions, the soil variations, soil moisture variations, very quick. Within that, the suction sensors cannot, detect the values, right? So if you are thinking that, okay, I'll put a one tensiometer in the landslide or slopes, it's not possible, right? It doesn't give a correct result, because continuously water contents will be changing. Night will be different, morning will be different. Within the daytime itself, the variability might be there. RH, temperature, water content, etc., rainfall, etc. There is a wonderful method. These are all very old methods derived in soil science. Nothing to do with geotechnical engineering. Geotechnical engineering, we've been using conservative designs, and in soil science they came up with amazing techniques. Okay. This is a simply same HAE disc. What we saw that when the water column negative pressure becomes more than 100 or so, then the vapor, cavities are developing, right? So what they have done? Okay, I'll do something. Suction is what? UA minus UW, right? So if UA is constant, that is what is the problem, right? UA is 101.325. At mean sea level. If this is increasing, again it is coming down. So what if I increase this fellow? That's the concept. Axis translation is, instead of controlling the UW or something, you control UA. So they connect to like a cylinder or something. We have cylinders, right? At home we use cylinders. Just like that, they connect. They increase the air pressure here. So that's it. When you are increasing the air pressure here, and UW you can control or keep it at 0. Now you are changing UA minus UW. Suction itself is getting changed. So problem is with the atmospheric pressure, right? If atmospheric pressure is elevated, then there is no problem. So that is a concept in axis translation technique, but it's a, I should say, very, very time consuming, highly time consuming.
3 months for science.
Sorry?
3 months for science.
More than that it takes. Very difficult actually. So advantage is that this method is used for when establishing hydraulic conductivity function. Theoretically it is possible. Theoretically you can establish hydraulic conductivity function, HCF, K versus psi, or water content. Same method. Okay. Outflow technique or something they call it. It's exactly the same method, same equipment, but very, very time consuming and very difficult to do that. I think you would have seen the osmotic technique. A membrane, semi-permeable membrane, and you have, this is a PEG solution, polyethylene glycol, and the molecules have certain size, where I can control the size of the molecules. Also I can control the force of the membrane, right? So I don't allow the PEG molecules to enter to my the membrane. So within a membrane I confine soil samples. Now what is expected if the soil is wet, right? Initially fully saturated, water is expected to come out because PEG molecules are not able to enter. So the PEG solution concentration comes down. I can measure those concentrations. Yesterday would have seen Brix index or something, right? Light reflectometry. Using that I can measure the concentrations. Using that I can detect how much is the reduction in the concentration, what is the suction, because the equilibrium or chemical potential of this one is known. Based on the chemical potential I can measure what is the suction inside, because suction here and outside it should be same, potential should be same, right, for both at equilibrium. So that's what I do. Even we have done for compacted soils by varying different membranes, by varying different PEG solutions. We have done a lot of tests. In fact, my first student worked on this, several compacted bentonite samples. This one also might have been demonstrated yesterday, dew point potentiometer, which exactly works on measurement of dew point, relative humidity and temperature, right. So essentially if you take a soil sample and then bring it here, it tries to evaluate what is the vapor pressure, right. So what it does, if the soil sample has certain UV, it tries to cool down wherever the formation of dew takes place. So that is the point dew has formed, right. So initial temperature was known, so it can evaluate UV. If UV is UV is known, you can understand what is the RH. If RH is known, because at what temperature the UV sat is known, right. Any given temperature the corresponding UV sat is known. UV by UV sat itself is RH. If RH is known, temperature is known, using the Kelvin's equation you can evaluate, from the Kelvin's equation you can evaluate suction, right. So this is the method it uses, but I don't have slides, but for a higher RH, 99.99, 99.9, the measurable suction is very, very difficult, it's highly sensitive. So beyond 2000 kilopascal, detectable suction is beyond 2000 kilopascal. Osmotic technique is for less than 2000, 3000 kilopascal. This method is good for beyond 2000 kilopascal. Similarly, vapor equilibrium. Yeah, I do have, here sensitivity is very high, right. So here 99.9, 98, all those things are here. So you can't measure. The variation is very less. Here variation is good. With temperature it's not sensitive. So this is a WP4, and this was already mentioned because we discussed the change in the RH due to presence of salts, because chemical potential of the water decreases with increase in the salts content. Therefore, based on that we actually have salt solution placed here. Under the same vapors the samples have been kept. So we are trying to equilibrate, right. So if the salt solution, if it is a water, then soil get wet. If it is K2SO4 or something, and if this is a saturated condition in the beginning, then water content will decrease, right. We did with the compacted samples in this manner, right. We actually continuously, the vapors have been flown to the both sides of the samples, and this is how the compacted samples, the SWs have been established. There is a simple method also. I am sure most of you, some of you who worked in unsaturated soil mechanics would have definitely used it, which is a filter paper method. Filter paper, just like the porous stone, which has kind of uniform pores, the SWCC of this particular filter paper is established. Whether it's a Wattman filter, that means it has particular size. For that, this is already established. How did they establish? They use vapor equilibrium, right. Pressure plate, amount of water droplets that come out is difficult to measure, right. So some of the methods which I described previously, you would use that to establish the SWs of the filter paper. Now you keep the filter paper either in contact or away from the soil to evaluate the suction. If it is in contact with the soil, you will evaluate matrix suction. If it is away from the soil, you will evaluate total suction, because it comes in equilibrium with the vapors, right. Yeah. So this is the total suction measurement. So these are some of the methods which are commonly used, like negative column, tensiometer, range. But range is, that can vary. I just gave some numbers, general figures, but it can change depending on where you are located, elevation, right? And axis translation around 1500 because 15 bar AEV is used. If your air entry disk is of capacity only 2 bar, range is only 200 kilopascal. So osmotic, even we went beyond this. We use certain membranes with which we went up to 7000 kilopascal. Dew point potentiometer beyond 2000. So it also takes a lot of time, and you can't use compacted samples, correct? Because you need to place inside. The small samples you have to place, it is not possible with the compacted samples. So laboratory methods, these are all laboratory methods. Tensiometer could be field method, vapor equilibrium lab method, and non-contact and contact filter paper, right? Any questions? One by one, maybe, yes. Huh? Mike.
In the contact filter paper method, when do we terminate the test? Like this is sandwiched in between. So how do we know that there is no change? Is it that we just have to keep it for a long time?
Yeah, keep it for very long time, and we need to sandwich between other, 2 more filter papers or something at least we keep, because otherwise soil particles will come in direct contact with the filter paper. They clog the filter paper, and there will not be any water exchange that may not take place. So therefore, generally we keep more number of filter papers. But problem is, when you are going for smaller and smaller water contents, how do you measure weight, right? So there are a lot of issues, of course. I never use filter paper, although this is very simple to use. Simple to use, but complex to
Measure.
analyze the readings, right? Yeah.
Yes, sir. One doubt has solved. The other is like, what is the significance of this axis translation term? Is it something with a stress tensor or something?
No, the axis has been changed. We were actually thinking about UW, etc. Now they moved to UA. They started controlling UA, right? The axis of control point has changed. That's how they named axis translation. Yeah. The same method is used for hydraulic conductivity, which is called multi-step outflow technique. So same method. If I have slides, I'll show you. So this is the these are the data on bentonite sample, which is starting from slurry state, right? When initially slurry state was kept, and we analyzed, and these are the readings we got when we merged with the VSC, right? This is with the VSC. Volumetric shrinkage curve, I showed different methods in the morning, I think, right? So we found that Claude method is the best method, and we got very good data for the bentonites. This is a powder bentonite. Initial state is at liquid limit nearly, right? This Gapak is my first student, Yagam Gapak. So yeah, hysteresis also we estimated, and some of the models, today it was discussed. I didn't discuss any of the SWCC models. I could not get a time to discuss. So that's why this extra class, you may think, So, so this is the Richard equation. Richard equation in original form, not even an original form, maybe, yes. So you will have theta and psi, both will be the dependent variables. So here, these two are what we are trying to evaluate. One is this one, other one is this one, right? This is one constitutive relationship, SWCC. This is another constitutive relationship, hydraulic conductivity function. I don't know whether to call constitutive or not, because constitutive generally between two state variables. Hydraulic conductivity, I don't think it is a state variable, therefore it may not be a constitutive but a relationship, variation or functional form of hydraulic conductivity. and this is a specific moisture capacity, the slope of SWs is itself. Okay, and you will interestingly get the k times, if you bring theta psi out, you will have theta by dou theta by dou z, right? In that case it becomes k times dh, if I write in terms of dh, dh by d theta, this is dou theta by dou z. This particular thing has units of what? This is meter per second, this is meter, that is a diffusivity, meter square per second, okay, which has some significance. So I think Professor Claudia showed the Brooks-Corey method for hydraulic conductivity estimation, but actually this was given initially for SWCC, and same thing has been adopted for hydraulic conductivity function. So simple models are there, like this is a Van Junichten model. So essentially what we are trying to do, we have lot of data, right? Experimentally we are measuring data, theta versus psi. We are trying to fit equations or empirical forms to predict continuous observations or continuous data, because what happens, to solve this expression you require a continuous function k of psi or psi of theta in a continuous form you require. You can't use a discrete data here to solve this one, so you require predictions. So models are there, so like Van Junichten, Brooks-Corey, Friedland-Schink, these are some of the models we often use. Okay, I will not go detail which is better, which is not better, etc., but there are models. There are a number of models, like as I said. On the other hand, for the hydraulic conductivity function, also you have some empirical models. In fact, you require more number of models for hydraulic conductivity function, because it is very difficult to estimate in the laboratory or in the field. Most of them are not accurate also. We may estimate and we get some data, but then it may be accurate or may not be accurate due to some limitations. These are some of the models. Some of them are empirical, some of them are macroscopic, like Brooks-Corey, where with some parameters which is related to pore size distribution they are trying to evaluate, they are macroscopic. Empirical are purely based on fitting the data, right? There are some statistical models like Hagen-Poiseuille's or Childs and George, what she was mentioning. These things could be used to evaluate the hydraulic conductivity function from the SWCC data without even fitting using Van Junichten or something. So this could be used. In fact, my regular classes I saw this one, and in fact I think in NPTEL also it should be there. Okay, so Burden Moolam, here you require models, like Jackson also is one of the models which is derived from Childs and George, and these two models you can integrate with Van Junichten to get analytical expressions for hydraulic conductivity function, right? So this is what we are doing. You have SWCC using retention models, water retention models, I mean to say SWCC models. We are getting a functional form. From there, using statistical models, we are predicting the hydraulic conductivity function. We use in the modeling of infiltration or evaporation or whatever it is, right? For evaporation, we might require drying data. We may require wetting data for infiltration, right? I just want to mention, because today morning after the discussion I thought I'll just quickly mention how the Richards equation has come. Although this is 19 and 11, I don't think there is a replacement to this, but there must be, there should be. But at least this is good for most of the soils. Even expansive soils are confined, there might be expected some changes, but it is good enough what it contains is just like if you know the derivation of consolidation equation, there is a derivation, right? So which is derived after this, that is in 1920s, 23, 27 sometime by Terzaghi, consolidation equation. This is derived in 1911, 11. Exactly the same. There he plays with the state variables and then brings those u values, etc. For that he uses additional one constitutive relationship called sigma dash equal to E, sigma dash equal to function of E. That is one constitutive relationship to change the variables. Otherwise, if you don't change the variables, exactly the same. You have mass conservation equation, this is mass conservation equation, right? After this Darcy's law, then you got the expression, that's it. That is your Richards equation. Fine. There is one old derivation for estimating the diffusivity. Diffusivity I just defined, k times dh by d theta, slope of the SWCC, right? This is by Bruce and Clute, 1956. Please remember the date, 1956, long back. Using the Boltzmann transformation, using the theta variable, so he converts psi also into theta, and then he does this. He gets the diffusivity. Now, if I have SWCC, which is psi of theta, if I can measure this, can I get k? Yes. So that is one possibility. I took a soil sample. This is our work. This is bentonite, right? Bentonite compacted at different densities, starting from 1.2 to even 1.8 gram per centimeter cube dry density, and connected to reservoirs, water reservoirs. So water is flowing, you could see water is here water is here. So there is a wetting front which is moving in the soil samples. Then what I do, I actually extract the soil samples. I push from the dry side, from this side. I actually slice it. If you think the water distribution is 1D, maybe it distributes because this is the column. If it is connected to water reservoir, you expect that the flow distribution is something like this or something like this. If that is so, if I cut here and here, there will be difference in the water distribution. If I see the core and periphery, almost the same. That means water distribution is going like this, right? I require minute details to use my 1D model. SWCC was independently established as I shown previously, Weber equilibrium, osmotic methods, etc. And I got the parameters. So these are different dry densities, the VG parameters, alpha and n, FX parameters, Fredland and Shing, alpha, m, n, Cr, which has 4 parameters. We evaluated. Even R square is also very good, right? What I get from here? Water content variation with respect to space and time. If I do multiple samples like this and connected to heads at different time periods and I sacrifice the samples, I expect that the moisture movement within the soil sample at different time intervals and different depths, lengths also, distances also from the reservoir. So these are data what we got. What I can do, I can solve the Richards equation because I have the k function. Sorry, I don't have the k function, but I have SWCs. I can predict the k function using statistical methods like Moolam, Van Jenisten Moolam, Van Jenisten burden. These models are there. Similarly, Fredland, Shing, Huang or somebody, WXH Huang. These guys have given a different hydraulic conductive function. We have used all those statistical models to predict the hydraulic conductive function. We inputted the HCF and SWCC in the Richards equation. If we try to predict, look at the predictions. The data is here. The predictions are here, right? Not this one, this one. Van Joosten, and this is Fredland. What does it mean? Either Richards equation is not fine for this, or K functions are not properly evaluated for using the statistical models, because SWC is measured. SWC is measured, and then we have a measurement of flow, transient flow. What went wrong? Either Richards equation or K function, HCF. Right? Richards equation probably fine, because volume change is not allowed. Here it's isochoric conditions. In the column, we don't allow the soil to expand. Okay? Something I missed. Yeah, we have these predictions based on determination of the diffusivity from the earlier method what I just showed you, the Clute, Bruce and Clute. Using this particular method, we evaluated the diffusivity, because you require what? X by root T and theta. So based on that, I can evaluate diffusivity. I know the diffusivity, I know the SWCC, therefore dH by d theta is known. I can evaluate K. So that's why if I evaluate the K, our predictions are better, right? And using the instantaneous profile method, there were publications already where they say that the hydraulic conductivity function started increasing beyond certain suction, which is not possible actually, but it was justified that there is a mineralogy change or something. Therefore, we evaluated the mineralogy also. Nothing happens here. There is no change in the mineralogy except the pore size changes are happening, right? So this is there, published in Geotechnical Environmental ASC. I think I thought of covering the last portion because there are methods to evaluate the hydraulic conductive function apart from multi-step outflow technique and other things. So any questions? Instantaneous profile method, which directly uses the Darcy's law. There is no mass conservation satisfied because it doesn't use Richards equation. Okay. Any questions? At least got some names of the methods so that we'll understand when we go to field or laboratory. Yeah, let's move then. Thank you so much. So we are moving to the ground where we are going to measure the flow, transient flow data using double ring infiltrometer. So therefore today it will be off from now, and thank you so much. What is it? Taros. What does it do? Don't tell, give me the suction measurement. Same issues. Same issues. So it takes very long time to establish the equilibrium. Papers are there. Published by Professor Tripathi et al. I guess, in Indian Geotechnical Journal. And later on we have some works also. Yeah. So measuring range is quite high. Almost it goes to the several hundreds of MPAs, but then it takes very long time. Yeah. Thank you so much.